Boy, the light makes neat colors.
Yeah, doesn't it make pretty colors?
Yeah.
Yeah. Well, let me turn the lights back on again because I want you to understand that we're going to be playing with light. And do you know about the different primary colors?
Yes.
What?
When you work with paints, primary colors are red, blue, and yellow. And when you work with light, the primary colors are red, blue, and green.
Right. And how did you know all that?
Well, this year in science class, we did a unit on optics, and we worked with color filters and mirrors.
I see.
But we didn't get as many pretty colors as this
Well,
one.
that's because I have 3 different colored light bulbs.
Right.
And how come we don't see all the various colors right there?
Because when you mix all those colors together, you get white light.
Right. So now I'll turn the lights down again and give you a series of tests.
Okay.
Here is a broom that will work to cast some shadows. I'm going to turn out one of the light bulbs. You tell me which one.
I think you must have turned out the blue light bulb.
Why?
Well, because to make this color here, you need red light, and to make this color here, you need green light.
Right. Now I'm going to turn it back on and watch what happens to the colors. I think you already know, right? Watch.
It goes back and it gives you full 3 colors, and it gives you a yellow, a violet color.
Yeah, it's called magenta.
And this one over here is almost a turquoise.
Yes, and that's called cyan.
Oh, I see.
Okay, and now I'll turn out another one.
Okay. That must have been the green light, because here you need red, and for this light here, you need blue.
For that shadow, right?
Yeah, the
now,
shadow.
when I turn the lights back on, watch. When I turn them all on, we'll go back to the same 3 colors again.
Yeah.
Obviously, the last one.
Red.
Right, yes. Okay, now, I don't know whether you were able to do this in class, but this is kind of fun to do. What you do is you get a piece of cardboard and drill a hole in the middle. Notice the light on the cardboard is what?
It's white,
because
of the mixture.
Right. But now you put a hole through it so that when you hold it up like this and look at it, you see all kinds of weird colors because you're combining, in some cases, blocking some of the light, in other cases, letting it go through. So look at what you get.
Oh, that's neat. You see the cyan and a blue.
Blue with a red circle.
Right, a red circle in there, a green circle there, a blue circle in there. Oh, and there's the magenta
There's
up
the
there.
magenta there, right, yeah.
And a yellow
Yeah.
or green under my shadow. And a red here.
Okay, so you see how much fun it is to play with the primary colors of light.
Yeah, this is neat.
Now keep stirring, Evelyn, because in there are 2 boxes like this, about 2 pounds of cornstarch and 3 cups of water. So I want you to stir it all up real good. You seem to hesitate at the bottom. Why?
It's really hard at the bottom, and
That's because it settles down. That's why I want you to keep stirring it.
and at the top it gets real creamy.
Yeah, it looks good enough to eat, doesn't it? Well, we're not going to eat it. What we're going to do is you keep stirring. We're going to pour it into that tray. And as soon as we get a nice layer on the tray, then I want you to come over here like this and take your hand and go like that.
Really?
Yeah. What's the matter? You think it's going to splatter?
Yeah?
Well, watch. I'll do it first. And you'll see a very remarkable property of cornstarch. Are you ready?
Yeah.
Where'd you go? Come back. Look at that. Now, the reason why this works is that cornstarch is a very unusual kind of molecule in that if you don't put much pressure on it, it's very runny. You see how runny it is? But when you put pressure on it, the molecules tend to link together to form long chains, and they become almost like a solid. In fact, they're now down at the bottom, so I'll stir it all up, and then I want you to do it. Okay?
Okay.
The harder you do it, the better it is, because the more pressure you put on it, why, the more like a solid it'll become. Are you ready?
Yeah.
Okay, one more. And Evelyn, down real hard as you can with your hand. Go! Okay.
That's weird.
Isn't it? See how watery it is, and yet it didn't splatter one little tiny drop, except where I dripped over here. Come on over to the sink, we'll clean it up. And do you remember now what the ingredients are?
Yeah, 2 cups of cornstarch,
And that's 2 pounds
Yeah, and 3 cups of water.
of water. You stir it up real good, then you can slap it like that real hard, and the harder you slap it, the more like a solid it becomes, even though it is a liquid. Ordinarily, farmers need the rain to water their crops, like this corn. But to keep the rain off the corn is the purpose of these 2 large buildings at Michigan State University's research farm. You see, scientists are trying to find out what is the least expensive but most effective way to irrigate corn. They want to determine the exact amount of water the corn needs during each stage of its growth. Rain would ruin the experiments. So when a computer-run system senses the tiniest bit of rain, it starts up motors that move the 2 structures slowly down the track towards each other. The 2 buildings are actually separate halves of a single barn that, when closed, is one of the largest structures in the world. It's called a rain-out shelter because it keeps the rain out. The barn allows the scientists to grow crops under natural conditions outdoors on a scale impossible to duplicate inside a greenhouse. Farmers will know the most efficient ways to irrigate their corn because scientists have been able to keep the rain off the test field with the huge rain-out shelter. Rhea, do you know what a pendulum is?
Yes.
What is it?
It's a weight at the end of a
Do
string.
you see a weight at the end of a string here?
Yes, right
Yeah.
here.
And you don't see any other pendulums, just that one?
No.
Actually, I think you'll be surprised because there are more sort of things that go through periodic motion than you realize, because that's what a pendulum does, right?
Yes.
Give it a swing. And its period is 1, 2, 3, 4. How do you change the period of the pendulum?
By the length of the string?
Okay, change it. Now it goes faster, right?
Yeah.
Okay, now let it down. Whew, now it goes slower and around in a circle. Matter of fact, I wanted to illustrate that because that's what most people think of when you think of periodic motion, the pendulum going back and forth. But there are other types of devices that have regular beats like that that aren't pendulums. Here's an example. Looks like a pendulum, that there's a weight at the bottom, but instead of swinging, watch what happens. Okay, give it a little pull down. See how it's going through periodic motion?
Yes.
Isn't it? How do you suppose you change the length of the period?
By changing the length of the spring.
The spring, right. Yeah, okay, I'll try it up here. Sure enough, it goes faster, right? Yeah. Then I don't know if you've ever taken music lessons, but if you had, you would recognize what this is, I think.
Yes.
You know what they call it? Metronome? Yeah.
Yep.
And notice, where's the weight?
It's at the top.
Right, well, in the pendulum, it's at the bottom, right? So this is sort of an upside-down pendulum. How do you change the period?
By pushing the weight down.
Okay, try it. Definitely, right?
Yes.
Okay, then come on around over in the back here, because I have a special kind of metronome, if you want to call it that. See this?
Yes. It's a saw.
Yeah, saw. And I've got it in a vise, and I've got this black tape on it so we can't cut ourselves. Give it a little push. Yeah, you see how it's going through periodic motion again?
Yes.
Sort of like the metronome, isn't it? With the weight up on top. Here, let me get it down. Because you walk right by another example of something that is periodic motion. See that spring? Give the end of it a little push. Not too hard. Just a little bit. There.
Looks weird.
Doesn't it? Would go like that for 15 minutes if we let it go, because it's a very efficient method of transferring energy back and forth. In fact, I got this from the inside of an alarm clock, but it illustrates the motion of the hairspring of a watch. Have you ever had a watch that you wind up?
Yes.
Okay. Inside is a hairspring, something like this, that's keeping it in time because it has that regular periodic motion. Then you walk right by this one too. If I hold it up for you, you know what to do with the buttons? Yeah, it's a stopwatch, right? And most people don't realize, but inside there's still something vibrating, even though this is an electronic one, because inside is a crystal. that when you put a current on it, vibrates at a very specific frequency, and they can now use it to count seconds and hundredths of a second, even thousandths of a second. Scientists use that system all the time. Well, when you first started, you saw only one example of periodic motion, and now how many are there?
There's 1, 2, 3, 4, 5, and 6.
Right. See, Laura Lee, out of an ordinary piece of paper, I've cut out sort of a four-pointed star. Okay.
Yeah.
What I'd like you to do, though, is take yours and follow what I do. Bend it right along like that.
Okay.
Okay.
Yeah.
And then bend the next one. What you're doing is making a sort of a paper flower.
Yeah.
But unlike most paper flowers, this one will actually open up like a real flower.
Oh, wow.
Okay, then push all the pieces up like this, so they're all together as close as you can get them like that. Then what you're going to do is put them on some water. Okay, ahead, put yours right in the middle there.
Okay.
Here, you can try that one too.
That one's opening. Yeah.
Yes, you see how it's opening, sort of
Yeah.
like a real flower?
Yeah. What causes that to open?
Well, paper is made up of a bunch of fibers that are all sort of twisted together and have a nice smooth surface on it so you can write on it. But when you put paper in water, or water gets around it, the water goes in between all those fibers and inside them and swells them up. And that's what's making it open, because it's swelling all those fibers around by the fold there.
Oh, yeah. Do you have to put anything in the water to make it open?
No, just ordinary old water. So you have to try various kinds of paper that you might have around. You make a sort of four-pointed star, and you can make a paper flower that opens like a real flower.
It's really neat.
Thank you. Giselle, this is a strip chart recorder that scientists use to record all kinds of phenomena, like the vibrations of an earthquake or speeds of cars and temperature and pressure and so forth. What are we recording?
My breathing.
Yes, you can see here as you took a breath in and let it out. That's sort of the normal breathing. There's where you probably said something right there, right? Okay, now take the deepest breath you can. Some change, right? And scientists can use the height of this to get an idea how much air you take in when they want to measure your breath. Okay, now breathe normally again. This time, after you see it established here, I want you to swallow. Okay, wait till this comes out. Okay, there's your normal. Now swallow. See what happened right there?
Yeah.
Try it again now. Swallow. There it is up there, see? When you swallow, you can't breathe. In fact, turn off the recorder. See the on-off button there? Fine. When you swallow, you automatically shut off the breathing mechanism.
Yeah.
You can see why, too, right?
Yeah, you might end up choking.
Right. You don't want the food to go down into the lungs or the air to go into the stomach. Sometimes it happens and people cough and try to get rid of it.
Yeah.
Okay. Now, I'd like you to run in place until you really feel your breath coming, and then put on the mask again and turn it on. What should happen to your ups and downs?
It'll be much shorter and like as if you're panting.
Why?
Because you're trying to catch up.
Right. So when you breathe, when you want to try to catch your breath, you breathe faster, don't you?
Yeah.
Okay. All right, go ahead, try it.
Okay.
Okay. Ah, you were right. Real short and not very deep, right? Yeah. Okay, now you're beginning to even out as you're catching your breath, right?
Finally caught it.
Yeah. Okay, now I'm going to turn it up so we can get it all out so you can take a look at it. Okay, tell me, what happened at all these various places?
Okay, I think here I started just breathing normally.
Normally, right?
And around here I started talking.
Yeah.
And about here.
Right.
And I started taking deep breaths over there.
Mm-hmm.
And then over here I swallowed.
Right. You see the other place where you swallowed? Yeah.
About
Another
there.
flat one, yeah.
Yeah.
Right. Then what happened?
And then this is after I started running.
Mm-hmm.
And they're much shorter. And as if you're in the mountains.
So I don't know if you've ever had a picture of your breathing before, but here you are with my compliments.
Thank you.
It's not a section of the Earth from outer space. The color has not been computer enhanced to increase contrast. The color is there naturally, even as you eat the specialized leaves inside a head of red cabbage. Here, Ben, take that quarter and see if you can drop it into the bottle.
Okay, that seems easy.
Yeah, should go in without too much trouble because the mouth of the bottle is very big. However, this time, here is a big embroidery hoop, and there's a little X that I'm going to put down here at the bottom. Where is it? You take the quarter,
Okay.
and when I find the X like that, you put it, there's a mark right up there, so that's right opposite the X. You put it up there like that. Now, whoop. What I want you to do is to yank the embroidery hoop out of the way by hitting it with your finger here as fast as you can. What should happen?
Well, I think the embroidery hoop will move while the coin will somehow stay in midair for a short second and you'll drop into the...
Right, because of a thing called inertia, the tendency of an object to stay still if it's still or move if it's moving. Okay, see if you can get the quarter into the bottle. Fast. Missed it.
Yeah.
Now, that was because I think you were a little off the center up on top here, and also because you should move faster. In other words, the faster you get this out of the way, why, the greater the effect will be.
Okay.
Okay. All right, put it on top, right on the line. Okay. Now, wait a minute. Fast. There you go. Okay.
Okay.
Relatively simple, because this time, there's a dime, put it in this bottle. Just barely enough room to get it in.
Yeah.
So see if you can do it again with the dime. Now, you realize how fast you have to be and how carefully you have to position the dime right on top of the line up here. Let her go. Ah, you did it the first time. Congratulations.
Thank you.
In a forest in North Carolina, Dr. Roger Powell nails a can of sardines to a tree. Why? Well, bears can smell the sardines a long way off. Since they're the only animals strong enough to pull the can off the tree, when Dr. Powell spots an empty sardine can, he knows a bear has been in the area. Students and other volunteers at North Carolina State University help Dr. Powell study the social behavior of the black bears. He demonstrates how to use the long pole, on the end of which is a syringe containing a tranquilizer that will immobilize a bear. First, however, they have to capture one. A special trap that won't injure the bear is hidden in the logs. The bait is more sardines. The bear in the trap is one they'd captured last season. It's tricky to jab the needle at the end of the pole into the bear's muscle. Soon after they administer the drug, the bear reacts to the tranquilizer. Dr. Powell makes sure the bear is unconscious and the team moves in quickly. A bandana is tied over the bear's eyes to keep out dirt and to prevent accidentally injuring its eyes. They shave a patch of fur so they can tattoo a number that will further identify the individual. Another team member extracts a small tooth. After analyzing it in a lab, they can estimate the bear's age. They even draw blood samples. Dr. Powell inspects the radio transmitter built into the collar. After checking this female's health, team members weigh her. She's just over 100 pounds. Later, by tracking her with radio, the researchers will be able to follow her movements and map out her range. Combining data on her with information from other radio-collared bears, they can determine whether she shares her territory with other bears. Wildlife officials can manage the bear population more effectively by using the latest scientific equipment and a sardine can nailed to a tree.
Yeah, I'm just gonna add a lot of salt,
Yeah, I would say that's a lot of salt, right?
and this is to add some red food coloring,
Okay.
and put a lot of grass in there to make a substitute for.
Now, do I understand you correctly that you're going to drink this before you're through?
Well, I might drink it, and if it works, and
If it works.
yeah, I'm just gonna stir it up.
Okay. Now what?
I'm gonna put this cup right in the middle to
Yeah.
collect all the purified water.
Yeah. Got a little leaf in the bottom. Okay, get it out.
Okay.
Okay.
Yeah.
Okay, now what?
To take this plastic
Okay.
and tie this string right around it. And just tie it nice and tight.
How did you know how to do all this?
I was reading a book called Improve Your Survival Skills, and I went on.
Improving survival skills.
Yeah. And I dug a 3-foot hole in the backyard
Yeah.
to try this out, but then when my dad found out, he took all the dirt and filled it back in.
Well, that's kind of dangerous to have a 3-foot hole in the backyard, right?
Oh
So
yeah.
that's not why you're doing it in a wash tub.
Yeah.
What's supposed to happen?
Supposed to happen is the water is supposed to evaporate onto the plastic, which stops it from evaporating away,
Yeah.
and then it's supposed to drip right to the middle and right into the cup.
Okay, how much water do you think you're going to get?
About half or a quarter cup.
Half to a quarter of a cup of water. And the whole day you're going to leave it here?
Yeah.
Okay. Well, when it's all finished, bring it in. Let me see it, will you?
Okay. Hi, Mr. Wizard.
Oh, hi, Philip.
I got the water from the sun water
Oh,
purifier.
great. You actually got some decent clean water in there?
I hope so.
Well, here, let's take a look at that because I wanted you to see what I was doing. I'm doing the same thing you were, sort of, right? Because I'm boiling water down here, and it's condensing up here in the top and then dripping down into that beaker in the middle. Same idea as yours?
Yeah, the difference is your heat is coming from the bottom and mine was coming
Your
from
heat
the
was
top.
up here, the sun, right?
Yeah.
But the idea is the same because you see, you were using evaporation, which meant that the molecules that were speeding up the most by the heat collected up on top and then ran down. In my case, I'm speeding them up faster. So evaporation and boiling are the same phenomena, only a different rate.
Okay.
Okay, let's see how you did with the water. Here, here. Pour it in, see how much you got.
50 cc.
50 cc's. How long did you let the thing sit?
All day.
All day? Was the sun out okay all day today? Well, how could you get more?
By making the hole bigger.
Yeah, if you had a big hole, the bigger it would be, the more you'd collect, right?
Yeah.
Yeah, well, anyway, what was in this when you started?
I used salt,
Salt,
food coloring,
red food coloring,
and grass.
and grass. And now you've purified it, you say.
Yeah.
Take a drink, see if it really is pure. Is it?
Yeah, it tastes like normal tap water.
Very good. Well, congratulations. You were able to purify water by using the sun to distill it.